Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, I'm going to be talking about the original IBM PC 5150. And on the bench I have my 5160, the XT, because my 5150 is broken right now, but these machines are good stand-ins for each other because they're almost identical. Now, when this machine came out in 1981, there are already a bunch of other computers on the market, like the Apple II, and this is an Apple IIc for illustration purposes, the VIC-20, the Atari 8-bit line computers, and a whole bunch of other things. And most of those computers, when you turn them on, they were pretty much ready to go and you could write basic code on them essentially instantly. But when IBM released the original IBM PC, that was not the case. And in fact, I can demonstrate by turning on this power strip here, which is going to turn on the monitor and its computer. And well, we'll just be able to see how long I can talk for this intro while this thing is getting ready to even drop you into BASIC. Now in this video, what I want to do is I want to try to address this problem. And while I know it's kind of silly because no one's really caring about the fact that this is slow, but the thing is, I think this was a kind of a point of contention for a lot of people with the IBM PC versus machines like the Apple II. You just turned this thing on and it was ready to go immediately. Look at this thing. It's going to take forever for us to even get to the basic prompt before we can even do anything. And that's not even booting an operating system off of a floppy disk. So what I'd like to do in this video is use some amazing open source tools that we have available to us. And I want to get the PC booting potentially as quickly as something like an Apple II or a Commodore. And let's see if we can actually get that to do it. And look, there we are. We're finally at BASIC. And I think I had to make a couple little cuts in this intro just because I messed up a couple lines here and there. That took a lot longer than the essentially instant on of something like the VIC-20. So without further ado, let's get to fixing the IBM PC. So you saw in the intro how slow the IBM PC boots up and how long it takes you just to get to the built-in ROM BASIC. I mean, that's just abysmal. Now, what's really annoying about this slowness is that while you can press Control-Alt-Delete to reboot the computer, and if it's working, the reboot process, the warm start, is relatively fast, doesn't take nearly as long. But the problem is with this machine is that there are plenty of scenarios where you might be running some software on it, disk-based software, that crashes in a way where you can't do Control-Alt-Delete. So you end up having to power cycle the machine, and then you have to wait through that entire process all over again. I have to imagine that people who own these computers back in the day and were running some of this software would have been really annoyed by the slowness. Now let me do a couple demonstrations again by showing you the exact boot process. And right now there's no floppy disk in the drive, and even though this machine is an XT and it's got the hard drive option, the hard drive controller is actually removed from the machine. So this thing is just a single floppy machine, and therefore it's going to work exactly like the IBM 5150 would, because that machine never originally came with a hard drive either. It's just a single floppy, dual floppy, or no floppies. No floppies being it would just go into BASIC directly. So we turn this thing on. And I have the switch for the monitor and the computer on the same power switch there, or power strip that is, so they come on at the same time. And what I'm going to do is try to turn off some lights here to maybe help that. Yeah, there we go. Now you can at least see that it's counting up the RAM. Well, this machine is fully loaded with 640K. Obviously, if it had less memory, it would count faster. And I think the motherboard that's in here, well, this is one of the older motherboards, so it can support from 64 to 256K of RAM. But of course, it's had a little bit of a mod done to it to allow it to go all the way to 640K, which is the most the PC architecture in real mode can actually support. So a lot of the slowness is the fact that, yeah, it's counting up the RAM, and it does it very slow, and you can't just push an escape key on the keyboard to skip over this. The stock BIOS, it just takes that long. And even worse is on the original IBM PC 5150, it doesn't even display a status of the RAM counting. It just shows you a flashing cursor until it's done. And there it is, ROM BASIC actually running, and we're up and it's working properly. And I've done a little bit of testing ahead of time in this video, so you don't have to sit through and watch this stuff run. To power on this machine, the XT, with single floppy drive, 640K and CGA, to get to ROM BASIC, that takes 52 seconds. 52 freaking seconds. Unbelievable. And don't worry, I'll have some tables to be able to look at all these times in an easier way than me just showing it to you on a post-it note. Now, back in the day when the IBM PC came out, there was IBM PC DOS, which was MS-DOS that IBM had rebranded essentially. And here's version 1.1. It's a very early version. This is only 180K or maybe even 160K floppy disk. It doesn't support folders. Pretty sure it doesn't support hard drives either. That was really DOS 2.0, and 2.11 was the most popular DOS that came out that supported all of those extra features. So what I'm going to do is turn this machine off, but I'm going to turn the computer on. There it is. And we will see how long this takes to boot. And of course, we have to wait through this extremely slow RAM counting process again. And yes, I can push escape, I can push the space bar. Nothing really does anything. There's no way to skip this. All right, so it counted the RAM, and now it's actually booting into MS-DOS. And there it is. Okay, that's because I pushed some keys before I had finished while counting the RAM, and I guess those got typed into MS-DOS. So that boot process takes 37 seconds. So oddly enough, it's much faster than running BASIC from the ROM. And I think the reason why is with the original IBM PC BIOS that's in this thing, sits there and it tries to read the floppy disk to boot an operating system, so read the master boot record on here, the MBR. And it must try multiple times. So if it can't find the MBR, it probably tries a bunch of times, it sits there for a while, and eventually it gives up, and then it launches the ROM BASIC. I'm just gonna put the keyboard up on the top here. I just wanna demonstrate that if you push Control-Delete, you can see that it's gonna boot back into MS-DOS pretty quickly. So it gives us the beep, the cursor, and now the operating system is loading. So the warm starts are bearable. Look at that. We're already in DOS. Not so bad. And that's because there's a lot more going on the cold starts with the stock BIOS than there is with warm. Now, if you can believe it, on the original IBM PC, not all of them had hard drives, and because of that, there were actually a whole series of games for the IBM PC that were called booters. And unlike most of the later games that came out on the PC that were just running MS-DOS and you could copy them onto your hard drive, run them from that, maybe they had copy protection or not, these were actual self-booting disks that weren't using MS-DOS as an underlying technology. They were just going directly to the hardware and loading the system. And this is very similar to how games worked on the Apple II and on a lot of other systems. So I've gone ahead and I made several of these booter disks, and I wanted to time how long it takes for these to work also from a power off state. So the power's off to everything, and I put in the disk for Alley Cat, which was a game that IBM themselves actually published. So I'm gonna turn the computer on now. There it goes. And let's see how long it takes to boot up. And we know it's gonna take a long time because it's gonna have to count the RAM again. It's almost done counting the RAM. I just want to add that the original IBM 5150 also was this slow at the whole boot process. And especially if you added extra RAM by a RAM expansion card, it was bad. Okay, loading Alley Cat. And essentially what I'm going to be doing is timing this from when the power comes on to when we start hearing the music, which is coming out of the computer right now. Now, Alley Cat boot process takes 40 seconds, so a little bit longer than PC DOS, which was 37, but both of those are faster than BASIC, which was 52 seconds. So hopefully that gives you a good example of the problem I'm trying to solve in this video, and I'm pretty confident I can get this thing working pretty much as fast as all of the other 8-bit computer contemporaries from 1981 with some changes to the ROM BIOS code on this machine. And to help facilitate that, I'm going to be using this IBM 5160 motherboard. That way I don't have to work on the actual computer because it's just easier to work on the bench with the capture setup and everything like that. And I'm going to be using the One ROM, which is a ROM replacement that's running an RP2350 microprocessor on here that allows me to quickly reprogram this with a USB cable from my lab computer to very quickly iterate on any changes to ROM BIOS code that will potentially speed this thing up. I'll show a little bit more about the One ROM in a second, but this is an open source project and it's absolutely fantastic. I really, really love it. And also for the BIOS code itself, I'm going to be using another open source project, the awesome GlaBIOS. GlaBIOS is a complete reconstruction of the BIOS routines for the 5150 and the 5160 and any other XT class machine. It is from scratch. It does not use any copyrighted code. Therefore, it doesn't violate any kind of copyright laws like a lot of the other BIOS codes that are floating around there, source code ones that is. So that's what we're going to be using to try to speed this thing up. And this will be a great BIOS when I'm done that I will be able to install into my 5150 and my 5160 so that I can get rid of this horribly slow boot process that these machines both have. But the question is, how fast can I actually get the boot process on this? And can I make it competitive with the fastest machines out there? Well, let's figure that out. Let me get set up by moving this computer off the bench and I'll get set up with my test setup. Let's start by going over all the parts I'm going to be using for this work. So this is an IBM 5160 motherboard. It's 256K to 640K motherboard, so this is a later version. It has 640K of RAM installed on it, so we have two banks of 256K plus 128K in two banks of 64K. Yes, it is empty RAM, but I haven't had any issues with this particular board. From a BIOS perspective, we're going to start with the stock BIOS just so we can kind of confirm what exactly is going on. This is the original ROM chip that was in this machine, but I do have the one ROM installed. And simply put, what the one ROM is a ROM emulator. And what I mean by that is it can emulate ROM chips. Both mask ROM chips like the 2316, 2332, but also EEPROMs like the 2708, the 2716, 27256. Just insert whatever you want to emulate and it can do it. And besides this 28-pin version that exists, there are other versions like a 40-pin version and a 24-pin version and even a 32-pin version for all the different types of ROM chips that might exist. We'll take a look at the GitHub repo in a moment, but I think this will be a perfect project for this type of work because I need to quickly iterate on the BIOS revisions that are going to be running on this machine, and instead of having to pull a chip out, erase an EEPROM, put it back in, programming, all that kind of stuff, this is going to allow me to do that incredibly quickly just with a USB-C connection. So besides this IBM PC motherboard, we're going to be using a stock CGA card, and this is the one I've shown previously where I've modified this with some bodge wires to try to speed it up and disable the flashing and stuff like that. I found this thing in a box of scrap at some point, and battery acid had leaked all over it and corroded the connector, plus some other stuff on here quite a bit. So after some treatment, and there's a second channel video, which I'll link to, this card works great, and I love this card because it just sort of shows how resilient hardware is. And then, of course, for testing the boot performance of things, I'm going to need to use a 360K floppy drive, and I'll just be using this one, which is also a drive that I fixed in the past. Notice it's missing two of the fasteners on the spindle here, and that's because I had to fix something under there and they were seized. And either way, this drive fully operates now, and that's a normal 360K drive. And the final component to this endeavor is going to be GlaBIOS, which I mentioned before. As it says right here, this is a modern, scratch-built, open-source GPL version 3 alternative ROM BIOS for the IBM PC, the XT, or any other 8088 clone or turbo clone type machine. And this particular project, along with the GlaTIC and GlaDisk, which is a clock driver and a high-density disk controller ROM, these were all created by Greg, who I had the fortune of meeting at VCF Midwest last year in Chicago. And in a car ride, we started talking about this particular project, and Greg gave me one of the versions of this ROM that was customized for myself. Or maybe I met him 2 years ago. I don't even remember at this point, but either way, that kind of got me thinking that maybe I could use his project, his BIOS project, to do this speed up project, because this has always been something that's super annoying about using my IBM PC or the XT. Both machines I like using because I really like how they look, but I really hate how slow they are to turn on, especially if you're iterating and turning them off and on. It's frustrating to no end. So since I'm already on the GitHub repo page for GlaBIOS, let's take a look at that, and then we'll jump back to look at the one ROM project, two open source projects that are going to make this really easy. So as I mentioned, it's a GPL version 3 open source BIOS, and that means that we can modify this to our heart's content. And Greg has created some really well-documented and easy to read assembly source code, because I will be editing assembly language here. And believe me, I am no expert in 8088 or 8086 assembly at all. In fact, any assembly language I am just basic knowledge of. But I think we're gonna be able to do some pretty cool stuff here by modifying this. So the current version release that it's at is 0.4.1. And what I'm going to do first is I'm going to load this stock release, and there's some pre-built versions here, so the IBM XT or the PC version, because there is a slight difference, not in performance, but in the way that the ROM BIOS reads the dip switches on the motherboard. So you got to use the appropriate one for the system you're using. So first what I'm going to do is I'm going to flash his BIOS onto this machine, and we're going to see what kind of performance improvements we can get just by using his BIOS on this computer. Because believe me, it will be faster, and it will be a lot nicer as well, especially for the original PC, because that BIOS, like I said, you just get a black screen with no information about what's going on, except it can let you get an error, and then it just starts to boot. So let me just download the XT5160 release, since this machine does not have the V20 installed in it. That's a drop-in replacement that can give you a little bit of performance boost. We're just going to download GlaBIOS 0418x.rom. So that brings me to the one ROM, the emulator that I'm going to be using to make this process so much easier. And I've wanted to come up with a project or a way in a video to show off the one ROM, because this is something that Piers has been working on for a while. And I gotta say, I think this was a perfect use case for it, at least for me. But let me tell you, this does so much more than what I'm going to be showing off here. So this is the GitHub repo for the One ROM project, the most flexible ROM replacement for retro systems using a sub $2 Raspberry Pi RP2350 or an STM32 microcontroller. Although Piers tells me that the STM32 one, while still supported, is end of life, and you really shouldn't use that because it's the Raspberry Pi version, the Pi Pico one, that's going to be getting all of the attention going forward. So Piers has a website for the One ROM, and it sort of talks about what this thing can do. So it emulates the 24 and 28 pin EEPROMs and mask program ROMs used in most of these old systems, like the C64, VIC-20, PET, the disk drives, the Ataris, Coco, BBC Micro, and so many others. And as I mentioned a moment ago, there are two other versions now, the 32-pin version and the 40-pin version. And the 40-pin version is good for the Commodore Amiga. It emulates 512K EEPROMs. So yes, you can do very quick and iterative development on Kickstart ROMs on Amigas or any other system that uses 30 or 16-bit ROMs in this 40-pin package. So Piers has developed some software to go with the One ROM. There's the One ROM Studio, which is a Windows, Mac, or Linux program that can actually help you develop and load code directly onto these. But there's also a web version of the flasher. So even if you're using something that you don't want to install software onto, that's what you can use. And that's actually what I'm going to be using in this video for doing all of this development work. There's a little bit of stuff you can't do with the web version, but none of that applies to what we're doing here. But just keep in mind, if you read the documentation on the GitHub repo, there is some stuff that you can only do with the studio version right now. Although I ran into a few bugs with the web version prepping for this video, and Piers has already gone and fixed those. And that's the great thing about the web version, is he can do bug fixes and you don't even have to reinstall any software. Now, there's a few things I want to mention about this 24-pin variant that I won't be showing off in this video because they don't apply to the 28-pin one that's on this machine. The thing about this one that is so cool is you can use one of these to replace multiple ROMs. But with the 24-pin version, there's a couple extra inputs on here, the X inputs. And if this were possible on the 28-pin version, you could plug in one of these and then run an extra baud wire that went to the chip select line of the second ROM. And the one ROM in the first socket could actually handle both of the ROMs. So it just saves you from having to buy 3 of these if you're trying to replace 3 chips. Where this would really come in handy is on something like the Commodore 64, where you could use a single 24-pin one ROM, put it into one of the sockets, hook up the 2 X2 pins, which are these 2 extra pins along the bottom edge of the header, to the chip selects of these 2 chips. And then, like I said, this single one ROM would be able to replace all 3 of the ROMs on the 64. In addition to supporting multiple ROM chips within a single one ROM, you can also do bank switching. So for instance, on the 64, if you want to support multiple character ROMs, you can do that by setting some jumpers on the one ROM itself or running it to a toggle switch. Now, I will mention one limitation to the one ROM right now, and it's not a physical limitation, it's just the software that's on here, the firmware that's running on here cannot program the actual RP2350 while the system is powered on. So if I plug a USB cable into this, it's in programming mode and is no longer serving up the ROM anymore. Piers is actually working on allowing that to work. There's some complexity to doing that, like you have to reset the system and stuff like that, but that is coming. So just know that there's more coming to this particular project than even is what is possible right now. So let me demonstrate how easy it is to program this thing. So I'm just going to plug a USB-C cable in to my lab machine, and we're going to hit connect, and there it is. That is the one ROM itself, and the motherboard, of course, is not powered up. So it's just the one ROM that's powered. And to program this thing with a custom image, all I have to do is select the model. So this is a Fire 28. The MCU variant is the 2350. It's going to load the current firmware, and we're going to say upload ROM image, and we're going to pick the GlaBIOS 0418X. Now, this is only an 8K ROM image, and what you can do is I'll select that. I want to select the type of ROM to be emulated. This particular ROM emulator supports all of these various types, but we're going to use 27256, which is what this motherboard needs, and we're going to build the firmware. And we got a little bit of an error there. That's no problem. So what we can do is we can just say duplicate that. We can build the firmware, and that's just complaining because it's an 8K ROM image I picked, and we're trying to load it into a 32K EEPROM. And we're going to hit program, and that's it. It is now programmed with that ROM image. Now, there's a little bit of a problem with what we just did, though. The GlaBIOS image I downloaded, as I showed, was just 8K. Well, the original ROM is 32K, and if we're going to run ROM basic, then I'm going to need to copy the basic portion of the original ROM into this image before I program it. Otherwise, this will work. It will load GlaBIOS, but basic is not going to work anymore because basic is no longer in the other portion of the ROM. The other ROM chip that's on here also contains part of basic and also part of the original ROM code, the original BIOS ROM code, that is. That won't be used with GlaBIOS, but we do need that basic code from IBM. Otherwise, we can't do our benchmark testing, how long it takes to get into basic. So what I did is I grabbed the original copy of that U18 ROM, the entire 32K ROM, and that's this .orig file. And there is the GlaBIOS file that I just downloaded. I just loaded that original ROM file into the hex editor, and this is a 32K file. And if we take a look, it's just a bunch of stuff that, we don't really see what this is. But if we jump up to address 6000, this 62X0890 Corp IBM, this is the start of the original IBM BIOS code. Not the basic code, the BIOS code. This is what begins executing when the system first powers on. Everything ahead of this or before this in this file is the actual basic code itself, the ROM basic. This is not necessary for the execution of this machine. You only need the top 8K of this file, and it's basically from 6000 all the way to 7FFF. And I just went ahead and selected it, and you can see that the length is 2000 hex. 2000 hex turns out to be 8 kilobytes in decimal. And just to make sure I am not talking out my behind, we can load the original GlaBIOS. And we can see that it starts all the way at 0, and there it is, GlaBIOS. And if we select all of this, and we go to the very end, and we go to the end, you can see the length is also 2000. So one way you can combine these is I can simply go back to this IBM ROM, we can just delete that part, and we can just copy that, and we can just paste it to the end of this file, and the cursor is at the end there, and now when I do that, we can see that the top of this file is now 7FFFF, and the length or the offset is now 8000. That's because I have the cursor at the very end. So this would actually work by doing this copy and paste manually. But you really don't need to do that. What you could do is just save the original 24K file with that extra 8K at the end removed, and then we could just concatenate that file plus the GlaBIOS, and that'll create the new full 32K version that we need. Now, to do that with any kind of Unix variant, you just use the cat command to concatenate those two files together. But to do that with Windows, you got to use copy/B, and then what we're going to do is add these two files, first the 24K one, and then we're going to add a plus, and then we add the second file, this one here, and that will concatenate those two together. And then what we need to do is output to a file name that we want to save this to. So I'm going to call this IBM 5160-GlaBIOS-basic.rom, and we're going to save these. And now we should have both of those concatenated, and we have a 32K file, and it's in the correct order. It's first basic 24K, and then it is the GlaBIOS at the end. Now on our programmer, I hit upload, and I'm going to pick that new file that's 32K in size. We're going to hit open. We no longer need to do the size handling because it is the correct size for the EEPROM size. We'll say build, we'll say program, and that should do it. So now we're pretty much ready for programming. The light is on very dim to show that it's connected to USB-C, but we can just unplug that. And now I just need to get this thing all ready to go for booting up by plugging in the power, plugging in the video card, plugging in all the various peripherals that we need to test this machine. We'll need a speaker so we can hear when the music works for Alley Cat and stuff like that. Of course, the last component we need is a keyboard, and I like to use this full-size AT keyboard just because I hate typing on the Model F. It feels great to type on, but it's a pain because of the layout. And this particular keyboard is the Wells American RT101FT keyboard, and it was sold at least by Wells American in West Columbia, South Carolina. And what I like about this keyboard, it's hard to see, but there's a switch down in there. It is AT and PCXT switchable. Plus, it actually has a pretty nice feel to it. I don't know if it's mechanical, but it feels really nice to type on. It feels very high quality. We should already be in the right mode for the RGB to HDMI. Let me turn the system on. There we go. That is GlaBIOS running when life gives you lemonade. And it's in cold boot mode, but you notice that booted a lot more quickly. Oh, I forgot to plug the power into the floppy drive, so that's why we got a post error. But notice the RAM check on this BIOS was so much faster. And of course, the other niceties is it actually gives you information about the system, so you can see how much RAM, the type of CPU, the type of video, if you have FPU or not, all sorts of good stuff. And at the bottom, we see the version string, and we are running 041-8X, the latest version. So hopefully that gives you a little bit of an idea, just plug the power into the floppy drive, that this BIOS on its own boots so much more quickly than the stock one. And I'm just gonna turn this on, and we'll see if this thing does go into basic, because the basic, ROM basic that is, should be working. So it just seeked on the floppy drive. We did not get a floppy error. And it takes a little while because it's trying to boot the floppy disk right now, but it's not able to. And there we go. Now we're in ROM basic. Incidentally, the mods I've done to my CGA card, well, they cause a little bit of snow, because normally what would happen is anytime you have scrolling, it would actually blank the screen. And I hate that flickering that you get on the stock CGA cards. I've disabled it. And I'll link to the video on the mods I've done to this card if you're interested in them. But that is why we get a bit of snow. So that's the trade-off. We get snow, but we also don't get that flashing. I'd rather have the snow. All right, so let's do a little performance benchmarking. First of all, all, I'm going to turn the system on from a power off state. Then you see that green flash or the cyan flash, that is the power being applied to the system, and it is now booting up. And I've already done this testing so I can tell you how fast or slow this all takes. But the first test we're going to do is just power on and go directly into the ROM basic, just like we did on the IBM PC. And that took 16 seconds, which compared to our last run at 52 seconds is a massive, massive improvement. Next up, PC-DOS 1.1. Let's see how quick this loads. I'll slide this into the floppy drive and I'll power off the system and we'll power this on. And with the IBM PC, this was actually faster because it didn't waste time trying to load the floppy disk and retrying a bunch of times. It just booted off the thing directly. And we went from 52 seconds to 37 seconds to get to the date prompt we're at right there. Well, with GlaBIOS, we are now at 13 seconds. So again, a massive improvement from the 37 seconds of the stock BIOS to 13 seconds, just simply by replacing the BIOS with this arguably much better ROM as well. Final test will be to load AlleyCat and time how long it takes to get from power on to the music, where we're actually getting the gameplay. So power off the system, power it on, cyan screen, and you should be able to see that before we were at 40 seconds to get to the game. There it is, 40 seconds. And now, well, it starts loading pretty quickly. And there it is, there's the music. And I can tell you that that took 16 seconds. So dramatically faster from the 40 seconds before. Funny is that took just as long to get to basic at 16 seconds as it took to get to AlleyCat. Now let me add that there probably are some other IBM PC XT BIOSes out there that would be found on clone motherboards, and I've shown some of those on the channel before. And if you run those, they might be faster than GlaBIOS as well, because GlaBIOS is doing a nice thorough RAM check and showing you that nice splash screen, and it's still a lot faster than stock BIOS, but you could potentially get even faster. But this is where I think with some modifications to Greg's code, I think we can get the computer running way faster. So let me get set up, I'll download the source code, and let's take a look at how I can edit this code and assemble it and get this loaded onto this machine. This is the source code package that I grabbed off the GitHub repo. And we have a make.bat, the GlaBIOS ASM or assembly file itself, and then a little utility that will convert the actual .com, which is what gets assembled, into a ROM file. Let me just load up these two files into the text editor. Now, right off the bat with the make file, one thing that you're going to notice that's interesting is that the assembler is using MASM, or Microsoft Assembler. It's discussed in the GitHub repo that the reason for that is, if you can believe it, is Microsoft Assembler version 5, which is an old MS-DOS version of the assembler, does the best job assembling the BIOS ROM file. The thing about these third-party or compatible IBM PC BIOSes is to make them compatible with the original IBM BIOS, all the entry points to the various interrupt routines, which are sort of the handlers for various functions of the BIOS, need to be at the exact same location in the ROM space as the original ROM. Otherwise, any program that will call these things directly by a memory location, thinking that they're on an actual IBM PC, are going to fail to run. So there's a lot of stuff that's going on in the assembly language to ensure that every single routine is in the exact same location in the physical space as the original ROM. And that introduces a whole extra layer of complexity, because if you're going to try to add a lot of functionality, which this BIOS obviously has, it has to do within the constraints of all those entry point vectors being in the exact same location in the physical memory space. And it just means that, well, you can't have freedom to shuffle around the ROM code as you see fit to make things fit into the address space, because this ROM is going to fit within 8K of space, as that is what's required for it to work on the original IBM PC 5150. And a lot of clones also have an 8K ROM BIOS. The assembly language code for GlaBIOS makes extensive use of a bunch of functions that a lot of more modern x86 assemblers don't support. And I actually had conversations with Greg about this exact problem when we tried to use some other open source alternatives to assemble the ROM. And I think Greg was able to get some of them working, but nothing really works as well as Microsoft Assembler version 5. Now here's the GlaBIOS source code, and there are some thanks and credits, and then we have build instructions, and there it is, MASM 5.0, which ultimately is what I use to do all the building. And then it goes on to kind of talk about all the various options and all the stuff that's happening inside the ROM. And as you can see, this file is relatively long. It's 12,884 lines of code, although it's extremely well commented. So even for someone like me, who doesn't really understand x86 assembly that well, I can make heads or tails of what is happening here. Now, as I'm making this video, I actually did all of the work to go through the original source code and try to optimize it as much as possible, or really take out as much things as possible so that the system would still work and be 100% compatible, but also be as fast as possible. And that's the glafast.asm. And what I ended up doing to try to make this easy for anyone else to follow is I made a new variable called max boot speed. And anytime that is set to 1, I change the code in specific ways. And I'll get into the optimizations and the changes that I made in a second. But what I'd like to do first is I'm just going to load the final changed ROM into the actual real hardware on the desk here. And I want to show you what speeds we're actually getting now after all these changes. So let's get the USB cable plugged into the one ROM. There we go, the light's on. Here's the file that is the fast version that has BASIC integrated into it as well as 32 kilobytes in size. We just have to pick a ROM type, 27256, build firmware, program. There we go. That should be programmed into the system now. So unplug the USB cable and let me power on the system. There's no floppy in the disk drive, which means it should boot directly into BASIC. And here we go, 3, 2, 1. So less left, well, there you go. We're in BASIC, ROM BASIC very, very, very quickly. Let me just show you that from scratch again. So the system is off, 3, 2, 1. Beeps. And after a few seconds, there we are in ROM BASIC. So power on to ROM BASIC now takes about 3.4 seconds. All the other timing I was doing before, I didn't even bother with the fractional seconds. Like I just sort of ignored those, usually rounding up or rounding down as appropriate. But now we're much faster than we ever were. So it actually matters the fraction of the second. What was our original time? 52 seconds to boot to BASIC, and now we are at 3.4 seconds. All right, let's try PC-DOS 1.1, and let's see how fast we can boot the system to a disk operating system. 3, 2, 1. The disk is already loading. There it is. We are booted up. So our original boot time was 37 seconds, and with GlaBIOS, we are at 13 seconds. And now we are at 5.4 seconds booting into MS-DOS. And we are fully in MS-DOS. This works just like it would have, but our boot time is dramatically improved. Okay, let's try the AlleyCat booter, which we can assume is going to be pretty speedy as well for the same reason that MS-DOS was speedy. So according to my post-it notes, AlleyCat took 40 seconds originally, and then I got down to 16 seconds when we were using GlaBIOS, the stock version. Now let's turn on the system, 3, 2, 1. Here it comes. Disk is already loading. And let's see what we get out of this thing. There we go, 8 seconds. I'll turn off the computer since it's noisy. It kind of boggles my mind that an original unaccelerated IBM PC XT, which is what we have here, can go from being off to running in a game in just 8 seconds. And that's loading it off of a floppy disk as well. I mean, I suppose even more amazing is 5.4 seconds to get to MS-DOS 1.1 as well. I mean, it's a very small MS-DOS, but still, off to in DOS is only 5.4 seconds, and that's loading off a disk. How cool is that? And of course, the biggest change is that BASIC improvement all the way down to 3.4 seconds. But wait, there's actually more. We can go even faster. Now, IBM PCs have a set of dip switches that allow you to configure things like the number of floppy drives and the amount of RAM and the type of video subsystem you have. These switches, which I know are a little hard to see just because of the glare, are configured appropriately for this system. 640K, 1 floppy drive, and CGA. But if we take a look at my IBM PC switch decoder, which is a little helper utility that I wrote a while back, we can take a look at the IBM PC XT and we can see all the switches. And the cool thing I like about this is I can never remember how to configure these switches. So this just allows you to pick like the number of drives, the video adapter, and that way, let's see, loop post, math not installed, and 1 floppy drive. And our amount of RAM is 640K, which I guess is that one. And that is the way the switches are configured on this machine right now. But the interesting thing is this operation mode, which happens to be switch 1. And on the original IBM ROM, I think what it would do is it would just continually run diagnostics forever, sort of as like a burn-in test thing. It was kind of useless in a way, so no one ever used that. And you always just had switch 1 turned off. Well, the thing is, on GlaBIOS, you can configure that switch to your own devices. And I currently have it configured so that if it's turned on, which is not normally the case, it actually disables the floppy drive routines entirely. So it doesn't even try to access the floppy drives. Normally, that's not particularly useful because, of course, you want to use your floppy drives, right? You don't want them completely disabled. But say you have a PC that has no floppy drives and you want to just go directly into basic, ROM basic, right away without even trying to access the floppy drives. Well, with my super fast ROM, setting that to on should have that effect. So we'll just flip this switch right here to the on position. And even though the floppy drive controller is still in the system, it should totally ignore it. And let's see how quickly we can get into basic now when I turn on the computer. 3, 2, 1. There we are. We're in ROM basic. It's that freaking fast. Yes, it is really, really that quick. It's basically almost instant on. I mean, once you see the cyan box appear, that's when power is actually applied to the motherboard from the ATX power supply I have. And it really only takes a split second for it to end up in ROM basic. That quick. Of course, we don't have any floppy drive support now, so we can't really boot an operating system off a floppy disk. But we can actually boot the system still, even with the floppy drive disabled, using an option ROM. So something I worked on a while ago and I never really made a video about was I actually came up with a way to boot MS-DOS from ROM as an option ROM. So this is the Monotech ISA double ROM card. I've shown this in the past because I used it with my XT IDE ROM just to quickly add that to a system that doesn't have it. But installed on here are two 28C256s. These are 32K each, so we have a total of 64 kilobytes of ROM space. And this is mapped continuously, so we have a continuous 64K. Well, I got to dig out my original files, but what I ended up doing is I ended up using some of the boot ROM code that Tandy was using to allow some of their systems to boot MS-DOS, and I modified it and actually altered the files that are on there so I could put my own stuff on here. So with this installed in any IBM PC compatible, it actually will just boot to the C prompt using MS-DOS 2.11, just like the Tandys do. And even with switch 1 set to disable floppy drives, the fast ROM that's on here right now is still looking for option ROMs. So it's spending a little bit of time doing that, and it should boot off of this. So I'm just going to pop this into the system like that, and let's see exactly how fast this boot process is. Okay, yeah, well, 2.3 there. I think if I time it, looking at the video capture, it will be about 2.2 seconds. Oh, the drive works. Oh, how interesting is that? So I just put in the AlleyCat disk. I don't know what this stuff is here. Disk copy does the deed on the AlleyCat disk. But if we put in PC-DOS 1.1, you can take a look at what's on that disk. So that disk is working fine. So I'm actually really surprised by that the disk on chip is able to access the disk drive, even though I thought I had totally disabled the disk drive subsystems entirely. But I guess it's still being set up, and all I really did disable is the actual boot attempt off the floppy drive. Well, with all that said, let's get into the changes that I actually made to make this thing so quick at booting into the operating system. Incidentally, I just want to show this table that I've been working on where I show the actual performance improvements. And I know I've been showing little clips of this in the video as I do these tests, but this is the spreadsheet itself that I've been working on. The C64 stock kernel actually boots into BASIC in 2.6 seconds. So already the super fast BIOS, when we have bypassed the floppy drive boot routine, is more than twice as fast as the C64 is at getting into ROM BASIC. And that's pretty staggering to me because, like I said in the beginning of this video, anytime you use the IBM PC, it feels so slow compared to these 8-bit computers that boot up and work so quickly. But yet, I think a lot of it is just due to the way the BIOS code is doing so much when you first power on the system. And if you take all that stuff out, which is what I've done here with my super fast BIOS, well, the system can actually work very quickly. You may also notice that on here I have the Tandy 1000 RL. Now, the reason why I have that is because VU Westlife did a video where he showed how quickly that system boots into MS-DOS, and it has MS-DOS 3.3 in ROM. And it's extremely quick. It gets you from powered off to in DOS 3.3 in 2.2 seconds. So I'm calling it disk on chip because it's very similar to the disk on chip ROM thing that I just showed you. And while I was able to match the speed of booting into MS-DOS 2.2 seconds, I was only able to do it if I had the floppy drive support disabled in the ROM, or at least booting from floppy drives. Now we know you can use the floppy drive once the system works, it just doesn't actually try to boot off the disk. Now, a few things to consider about the Tandy 1000RL is that it's an 8086 system, so I don't know for sure, but it might have 16-bit ROMs, which means the CPU is able to access the ROMs twice as quickly as a system that has 8-bit ROMs, which is what this uses. In addition, of course, this machine is running at 4.77 megahertz, and the Tandy 1000RL, I think, is an 8086 running at 9 point whatever megahertz. So it's basically twice the clock speed of this system as well. Possible the 1000RL also has 16-bit RAM instead of 8-bit RAM, which is what this has. That just all contributes to this processor being so much slower on this particular setup, the XT and the 5150. So because of the clock speed differences and potentially that 16-bit RAM and ROM difference, it's not entirely an apples to apples comparison. Tandy Radio Shack obviously spent a lot of time optimizing the ROM code to make it boot as quickly as possible, probably because one of their engineers was really annoyed at how slow the original IBM PC was at powering on, just like I was. So someone at Radio Shack obviously spent a lot of effort to try to make them boot as quickly as possible. And even the original Tandy 1000 boots pretty quickly compared to the original IBM PC. You just turn it on, it starts booting almost right away. Only the later systems had the disk on ROM stuff. The original ones you had to use floppy disk. But yeah, it was always a pretty fast booting system. And of course, because all the entry points to the various interrupt vectors and stuff like that were all in the same memory locations in the BIOS code, they were 100% PC compatible as well. To that end, here's the code, this glafast.asm that's loaded in the text editor. This is actually what I assembled and what is running on this machine right now on the one ROM. Before I go through all the changes that I've made to this to make it run as quickly as possible, or at least boot as quickly as possible, let me first talk about the environment I used to do this work, to do the testing and the assembly of this so that I could then try to run it on real hardware, which we're doing in this video. As I mentioned, you have to build this ROM using Microsoft Assembler 5, and other assemblers, like the open source ones, don't seem to work properly. So generally, you really do need to use Microsoft Assembler 5.0, or I guess 6.0 works, but I think Greg told me 5.0 is really the preferred version. So what I ended up doing is using DOSBox to install Microsoft Assembler into and use that for assembling the ROM. Because the good thing about that is if we open this, DOSBox can run at as fast as your computer can run, so you're not hamstrung by the performance of running Microsoft Assembler on a vintage PC. I could, of course, assemble this on any old vintage PC. It's just moving the files back and forth in the text editor and then testing the ROM and getting it working in an emulator or on real hardware. It's all a bit of a pain in the butt, and it would really slow down, especially for someone like me who doesn't really know what they're doing when it comes to assembly language. So there's a lot of trial and error to try to figure out exactly where I can save time and what I can do that won't break things as well. So when I run this, I've just created a little batch file here. So I can just type make. That is the wrong keyboard. I have to switch to this keyboard. So I type make. There we go. We can see we're using Macro Assembler version 5.0. And sorry, I was calling it Microsoft Assembler. It is actually called the Microsoft Macro Assembler, and I'm using 5.1, which seems to work really well for me. Don't worry about the segment near or at 64K limit. This is just because it's trying to assemble to a .com file, which is what you would normally assemble to that you could run in MS-DOS, but we're actually making a ROM file. So after assembling it and it links it, then we use the GLA2ROM program that Greg made that takes this exe file, the GLAFAST, and then it outputs the actual ROM image, and it makes the 8K ROM image, which is exactly what we need to actually run on real hardware. And the cool thing about this, of course, is all I have to do is make any kind of changes to this code in my text editor. And watch, if I just put some like garbage here, and then I try to make this again, it's going to give us an error. There's the error. Expected instruction, directive, or label, blah, 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 line 84. And that's because, of course, with DOSBox, you're able to mount the file system of your host computer directly into the DOS environment, which makes this in and out of the environment so easy. You don't have to spend time exporting, importing. It's just all instantaneous and automatic. So I just remove that bad line. We can do make. There we go. It just made with no problem. Now, originally when I was working on this, I didn't have the one ROM emulator that I have now to quickly load this into real hardware. I had to like program a chip, and it was just a pain in the butt. So I was doing a lot of the iterative testing using MAME. MAME has a pretty good 5160 emulator. It's not cycle accurate, but at least it would let me know if the system was working properly or not. So I created a batch file that will start MAME, but before it does that, it takes the GlaBIOS file that was output from the assemble process, and it adds the basic ROM to it, that 24 of extra K, so that I can run basic. Because of course, part of my goal here was to make it actually be able to go into ROM basic more quickly than the stock BIOS, like that 52 seconds. So if I run this, what it's gonna do is it actually copies those two files together to create that 32K file, and now it's gonna start MAME. And it will complain about the fact that the ROMs are incorrect. That's, of course, it knows the checksum what the original IBM ROM is, and the new one doesn't match that. But if I hit a key to start this, there we go. We're running the exact same code, that we are running on the real hardware right now. And it's a good test to see how quickly you can actually get yourself into BASIC or load software off the disk drive and stuff like that. In fact, let's take a look at the batch file that I'm using to start MAME. So there it is. It's concatenating those two files together as I showed earlier in the video. And then this is the command line that I'm using to start MAME. And it has a floppy drive controller installed and it has a CGA adapter installed. And right now I don't have a floppy drive inserted into the system, but I can easily do that by adding the -flop1, and then I can point to one of those booter images. So there is Alley Cat as an example. So we'll just save this. And now when I start the 5160, hit the key, loading Alley Cat, and I can hear the floppy drive coming out of the speakers. And there it is, running. So it was a really good way for me to test the iterative approach to speeding up the ROM BIOS code more and more. Okay, so finally, let's take a look at the changes I made to the ROM to speed it up. What I found doing, especially after talking to Greg, is that the reason why the IBM PC is so slow when you first power it up is because IBM did extensive and exhaustive diagnostic testing every time you turn on the system. Contrast that to the Apple II ROM. That does basically zero diagnostics when you turn it on. It does absolutely nothing to make sure the computer is working properly. It just clears the video screen buffer, sets up a few soft switches, and jumps you into BASIC or tries to load a floppy disk if the disk controller's there, and that's it. Commodore, on the other hand, does at least try to do some very rudimentary RAM checks, mainly to size the amount of memory that you have. But yeah, it's not much of a diagnostic, but it's more than zero. And that's why the Commodore 64 with 64K of RAM does take a couple seconds for it to get into BASIC. But IBM, on the other hand, you know, they were making mainframes. They had to be super reliable. These were like business computers, not just toys. So they built so much diagnostic stuff into the ROM. And while it's nice that it's there, it's also kind of ridiculous, especially because there's that switch 1 on the motherboard that could have easily just made it where you set that switch to on, which was not the normal position, and it would run all the diagnostics. Say you wanted to be very thorough about your computer, so it was ultra reliable. Set that switch 1 on, then turn it to off, and it won't run any of the tests, and it will boot quickly, like all the other systems. But no, IBM just made it where it always runs all the tests anytime you're on a cold start when you first power it on. And that's why you're sitting there with the longest RAM test and a whole bunch of other tests it's doing that just takes forever for the system to boot. So what I decided to do is, like I said, do what the Tandy Radio Shack engineers did and just remove everything I could that had to do with diagnostics. I just wanted to get the system set up and initialized so that the system would be able to boot properly, but not actually waste time doing any other checks. And luckily with GlaBIOS, everything is so well documented and so easy to manipulate that I was able to kind of pick through the code and remove everything under the sun that I felt was slowing down the boot process. And well, that resulted in the BIOS we're at now. So right off the bat, there are a bunch of configuration variables you have available to you when you assemble this ROM. Now, one of the things is this ROM is designed to work with all of these different systems and has a bunch of customizations to support things like turbo and this, that, and the other thing that the original IBM PC 5150 and 5160 don't have. It also can take advantage of the V20 for the special and faster instructions that the V20 has. So when you enable V20 support in the ROM code itself is actually optimized to use the V20 properly. That's not something that would happen with any other system because those ROMs don't know about the V20. So while the V20 can offer a little bit of performance improvement just in general running normal 8088 code, if you use the special instructions, you can even get additional speed. I'm not doing any of that here with this testing, so that could result in slightly faster speeds here, but either way, we're using 8088 and non-turbo, just running at very stock speed on stock IBM hardware. So if you just load up the stock BIOS, one that hasn't been changed by me, there are all sorts of options in here that you can manipulate and just assemble this yourself and customize it to your heart's content. And Greg put in tons of options to actually do a lot of these speed ups, even without massive changes to the ROM. There are a bunch of personality traits which affect how it looks when you first power on the system. And one thing to keep in mind, by the way, I just want to point this out now, is that CGA and the entire system is so slow. Anytime you're writing to the CGA interface, even if you're just writing a line of text, that slows it down. And the more stuff you're doing on screen, the slower the system is. And that's why you might have noticed when my ROM powered up, it just showed the RAM size and that was it. Didn't print anything else. Because I found that printing additional text slows down the system in a measurable way. And I was really trying to cut out everything I could to speed it up. Now here we're getting into some of the nitty gritty of the slowdown. These tests you see, instruction test, DMA test, PIC test, blah, 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 all this stuff, this all kind of came from It wasn't lifted exactly, but those types of diagnostics are all happening in the original IBM ROM. And you can enable or disable these simply by just changing these from 1 to 0 and reassemble the ROM, and those will be disabled. This ROM is written from scratch, so the actual test routines that are happening in these various tests were recreated and are not just copies of IBM's original tests. So it's quite possible that IBM's original code that was running these is even slower than what's happening here, which probably is the reason why just going to GlaBIOS speeds up the boot process so dramatically. And of course, a big part of that is also the RAM test. The way IBM tests RAM is relatively thorough, not the best, but not terrible, but it's also incredibly slow. So GlaBIOS implements a much more efficient way of testing the RAM, which is still really good, but it's just much more quick as well. You can also entirely disable the RAM parity checking, and I have to say, we'll see the changes I made in a moment. I did turn that off, but that doesn't actually affect the performance at all. That just gets rid of the whole parity checking thing, which, let's be honest, 99.9% of home computers when the PC came out did not do any parity checking. What parity checking is, there are actually 9 chips per bank instead of just 8, and the extra chip is used by a piece of hardware on the system to detect if potentially there's a RAM error. It's not perfect, but it can detect if you have a problem in one of your RAM chips or the parity RAM chip, unfortunately, because if it goes bad, it also will generate these parity errors. And the parity errors will generate a non-maskable interrupt, which will halt the system and then print that parity error message on the top of your screen. And well, that's the end of that. When you turn off the parity error checking in this ROM BIOS code, you can actually take out the parity RAM chip, which I think it's this chip on this motherboard, or it might be the one on this side. You can just remove them from the motherboard. They aren't even required, and you won't ever get those parity errors any longer. Another thing you can do is you can change it from a long RAM test to, I think, just a quick RAM test, and you can also do no RAM test. It doesn't even clear the RAM at all. I think if you turn on this option with a 1 and you have parity checking enabled, you'll get parity errors because you need to clear the RAM to set up the parity RAM at that extra bit of RAM. So you need to disable parity RAM if you're also disabling the clearing and the RAM testing. I'm pretty positive that Tandy 1000s do not have parity memory, and they also do not do any kind of RAM checking. They just quickly size the RAM, and that is it. They don't clear, they don't do anything. So it's essentially the same as turning off parity here with a 0 and changing this to a 1. You'll notice there's a bunch more settings. I won't really go into every single one of these, but you can see that turning off some of these is going to speed things up. Now, one thing I want to mention here is this IPL switch, the FDC IPL switch. Setting this to 1 is what changes the code to enable or disable the floppy drive. And that's what I'm using to be able to set that switch 1 on the motherboard to disable the drive. And here we are to Adrian's speed mod. So these are the changes that I started making to this ROM. So far, everything has just been completely stock. So I created a new variable called max boot speed. And if you set this to 1, it'll boot up as quickly as possible, just like we were doing on this. So initially setting this to 1 just sets all of these variables to these values. And it's kind of what we already talked about. I'm disabling pretty much all the diagnostics that I can, at least in these variables. I'm disabling the parity checking. I'm disabling all the RAM testing as well. So RAM test is set to none. I'm also not printing out any of that configuration stuff because that just slows down the boot process. And then finally, I'm forcing on that function to allow me to disable the floppy drives by setting switch 1. Now this alone, which anyone could have done very quickly and easily, results in a pretty good speed up. You don't really have to do too much to get it running pretty fast. Problem is, I wanted it to run even faster, and I picked through all the code, and I found that there was a bunch of other stuff that is still happening that I felt was unnecessary, and I just took it out entirely, essentially using the max boot speed equals 1, and then if-then statements to remove it from code if you set this to 1. If I set this back to 0, this should just assemble back to the totally stock version of this ROM. And by the way, keep in mind, none of these changes have actually been upstreamed into the code, although Greg has been working on taking a bunch of this stuff and putting it into the final code. So hopefully in subsequent versions of this, there will be like a super fast version of this where you can just set 1 variable and all of this will be done, all tested and working properly. So when you look through this, this is a bunch of configuration stuff for like the different types of systems. So none of this has anything to do with us. And it's a little bit hard to understand the way this code works because it does require thinking about all these like if-then statements that are in there. Essentially what happens with the macro assembler is when it runs through this, it parses it, it evaluates all these if statements and it creates a new copy of the assembly in memory, I'm assuming, and it takes out all the stuff that's just not necessary. So when I disable the diagnostic code up here by setting those variables, I think the final thing that's about to be assembled, it doesn't even have the instructions for any of this post stuff in it. Problem is, when you're looking at it in text editor, it is all there, and it can make it a little hard to decipher because you're wondering like, well, is this stuff, these like DB values, is this going to be there or not there? There's probably a way with a better editor or maybe some other tool to reevaluate this assembly file the way it's sit right now with max boot speed set to 1, and it could take out everything that's irrelevant, and that would just make it easier for me to parse through. But unfortunately, I don't know how to do that because I just don't know much about assembly. So this was all just done by me kind of looking at it carefully and analyzing to say, oh no, that's not even relevant because that's, you know, there only with another if statement. So here's an example, by the way, in this one macro, which is, what is this, set E flag. And this is a V20 optimization. If V20 is enabled, then we're using these ROR instructions to do some kind of shifting. Otherwise, instead of a single instruction for this rotate left or right, now we have to actually do 2 instructions. So it looks like on the normal 8088, or if you're going to do rotate right or left, you have to also have this move ahead of time. Now, I don't really know how often this particular code is called throughout this ROM BIOS code, but say it's used all over the place a lot. Well, we're saving instructions because, of course, 8088, it's a slow chip. It's a 16-bit chip running on an 8-bit bus, and that means that anytime it accesses RAM or ROM, it's doing multiple requests. But even worse than that, the address and the data bus are multiplexed. That means you have to do twice as many cycles for that as well. And therefore, if you have code and you're saving a single instruction, but you're doing it a lot of times, that can dramatically speed up code. Anyhow, we're barely making a dent in this code. I got to speed up this thing or the video is going to be too long. So all we're going to do is look for max boot speed in the code. And let's just quickly jump through them all. So this is the first one that we already talked about. That's just setting up all those variables. But then if we go to the next one, and what I ended up doing is I just sort of reassigned some of the color values. And that was only because remember how now when it shows the RAM size, it's a red color. That was just silly. I decided to do that just to kind of show, hey, we're running in the fast mode versus the green color that it normally shows. I think there would have been a better way to do this. It's like, if it's the max boot speed 1, those are the colors. Otherwise, it's the normal colors. But now we're getting into the meat and potatoes of what is actually the ROM code. This is not the macros. These are not any of those other like definitions. This is actually the code itself that is running. Now it looks like if I set max boot speed equal to 1, I changed the little logo from a heart, which is the normal little logo that shows on the banner, to the omega symbol. The thing is, I actually have the banner disabled, so this doesn't even do anything. So that's kind of silly on my part. And I made another change to the banner where if max boot speed is not set, then essentially it just says, you know, release under GPL v3. Otherwise it says super fast and unsafe. But again, the banner's turned off, so you don't even see that. That's bad on my part. These are optimizations that don't do anything. Okay, so but here we are to getting to an actual optimization that is running on this code. So right now, if boot speed is 0, which is just the stock setting, it does, I don't know, it's sort of like passing the values around, and then it does some initialization of some registers in the CPU. I decided to just remove essentially this part right here because it didn't seem like it's actually necessary. All I'm doing is just initializing all the registers with a 0. So it just takes a 0 and passes it through all of that. And I just eliminated some additional code. I know it seems kind of silly to do this type of optimization, but I found that if I could remove it and it didn't hurt anything, it actually sped up the entire process. And every little bit helps because the computer is so slow, which is why I kind of went through this and just removed everything I could. And I think originally I just took out this entire section, but it wouldn't initialize the CPU properly and the computer wouldn't run. So I found the bare minimum of what I had to do and I kept that in. And that's what I ended up doing with a lot of these optimizations. So I don't know why sometimes I did if max boot speed is 1, and then I had the code that I run, otherwise run the old stock code. And sometimes I had it reversed, where I leave the stock code here, that's the stock code, otherwise run the optimized code. My bad, just because I'm not a programmer, I did it kind of backwards sometimes. You can see down here, sometimes it's 0s, sometimes it's 1s. Okay, so that's the first optimization. Another one has to do with the way the base RAM test is happening. So essentially what the original BIOS is doing and GlaBIOS is it's really double checking that that first 16K of RAM is working properly. It does that initialization before the video is even turned on. So this is the original code. So max boot speed is 0, then yeah, it kind of does all this stuff and base memory, blah, 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 blah. And there's a whole bunch of kind of checking going on here. And it doesn't take a whole lot of time, but again, every little bit counts and all of this stuff just sort of does stuff. And I found it wasn't needed. So what's happening is normally it runs all of this stuff and there's a bunch of loops and things that are happening here. Well, when you're running with max boot speed enabled with it set to 1, what it's doing is then this else thing is running and all it does is just jump to base RAM 0, which is zeroing out part of that RAM, which does need to happen. So yeah, we're skipping over this whole part of the RAM check, which just helps speed up the whole process. The next optimization, and look at me using not equal to 0. So if it's set to 1 like it is now, what it does is it beeps very early on in the boot process. Normally the IBM PC doesn't actually beep until it's done all of its diagnostics and then you get a beep. And that's the way GlaBIOS worked as well. I like it to be more like the Tandy, where the beep comes immediately when you power on the system, and that's exactly how this is working now. So meep is a macro that exists already that does a very quick beep, and that is just enabled because boot speed, if it's not equal to 0, then it will do that meep at the very early on in the boot time. And I wrote that there, boot sooner to make the system seem faster. Yeah, it's silly, but I'm telling you, for me, I think it's pretty cool. That's why when I turn on the system, let me just do it right now. You're gonna hear a beep as soon as I hit the click. So 3, 2, 1. I mean, it's literally a fraction of a second after the power switch is turned on, that beep comes. And I like it. I like it that way. It's a psychological change that seems to result in the system feeling faster than it probably actually is. Okay, the next optimization is a stupid one on my part because basically if boot speed is equal to 0, then it's printing all this stuff, otherwise it's not. Now the funny thing is this is the same thing obviously as post banner equals 1 or not. So this is a dumb optimization and I already have it disabled by just turning off the post banner. So I don't know what I was thinking by this one. Next optimization has to do with setting up the LPT COM port timeout defaults. So the normal code is what we see here, which is this code right here. And then there's some game port stuff that's running, no game port, blah, blah, blah. We kind of have to follow this all the way down to where the end if is. I think all of this like parallel serial port checking stuff, this stuff isn't really needed. This is really just for the BIOS to be able to tell you like on that banner screen that COM ports exist or game port exists or parallel port exists. None of this actually is used by programs that use those ports. Programs do not expect the BIOS to say, hey, you have a COM port, you can use it, here it is. The programs just look for the COM port on their own. So what I ended up doing is there's the end statement. When you have max boot speed set to 1, none of this stuff runs. And again, it's quick, but anytime you're removing all those instructions, any kind of loops that are happening here, it helps. It speeds it up. Every little bit helps. So all of this detection routine is gone. And of course, because the banner's not printed, it's not needed anyways. I would assume if the banner were printed, but this were disabled, then you just wouldn't have any COM ports populated even if you had those COM ports. The COM ports still work, by the way. I did test this. It's really just a function of like what's happening on the BIOS boot screen. Here's my next change, and this is one that's actually a little bit contentious, and this is something that unfortunately isn't fully dialed in yet. I found after reading the code that quite a bit of time is spent on the keyboard reset routine. And this has to do with the fact that the Model F specifically requires a really long reset timeout. And I was trying to speed up how long this delay was running for. The original delay for the keyboard reset, I think, was like 1.5 seconds. So just that alone would take that long when you power up the system. And I remember chatting with Greg about this, and I think it was the Model F and maybe even the Model M, the XT version of the Model M, were just extremely finicky about this whole reset timeout thing that was happening. And even though this code is disabled, this stuff right here with this post keyboard test, all this part of the routine does is actually look to see if the keyboard is responding, like it's there or not. That's what gives you that 301 error code on the stock IBM PC. But the actual resetting itself is happening up above here. Yeah, post keyboard reset. This is not disabled, and I didn't disable this because if you disable this, the keyboard just doesn't work at all. So it sets up and clears the buffer. It does some stuff here to like signal the keyboard that, hey, you want to be reset, and it takes 20 milliseconds to do that. So the resetting still is happening, even if the test is not happening right there. And that's what I'm trying to do with this 40H to CH is this delay. If you try to shorten it too much, it seems to result in the keyboard just not working properly. Now we saw with this code running on this hardware with my Wells American keyboard, everything is working fine. But I'm quite sure that right now, the way this is set up, the Model F does not work correctly. And it looks like after the reset happens, there's that delay, the max boot speed delay. It looks like it still does some stuff looking to talk to the keyboard, and then it enables the keyboard. Keyboard enable, clear, low. I'm not really sure how much you have to do all this stuff because to be honest, if the keyboard's reset and it just sort of resets itself on its own, and by the time you get into basic or DOS or whatever you can type, who cares? You don't need to type anything before then. It's not like you can abort a RAM check that's not even happening anyways. So it's totally possible that there are more optimizations that could happen in this keyboard reset routine, which even the way I have it set here with this 40H delay, on max boot speed, it could speed up the process quite a bit. This whole thing though is a lot of the slowdown for the system initializing. And to be honest, if we took this whole thing out, the system would boot even more quickly without this whole keyboard testing routine stuff. Part of me wonders if we just do the reset routine and then do this keyboard happy part here, it should just enable the keyboard and call it good. You know what? Maybe I'm going to try this. Okay, we'll come back to this. Let me put a spot there. We'll come back and I'll edit this and we'll see if we can make this work. Next thing I had to do with the IPL jumper, that's the switch 1 on the motherboard to disable the floppy drives. It looks like that if that's set to 1 and the max boot speed is 1, then I'm just sort of skipping over all the floppy drive initialization stuff. I'm kind of amazed that it still works in DOS. So that's interesting. Again, I don't quite understand this whole boot process, so there's stuff in here that could be optimized to work better and be faster all the time. And then I also do something similar about this hard drive checking stuff, post HD check, but I felt this would allow you to like selectively disable it. The funny thing is, even with setting the switch to 1, which is actually qualifying this, which means this code is not running, hard drive still works. I can put the XT IDE in this thing and it still boots. And we were booting into MS-DOS using this disk ROM card too, which basically is emulating an 80H hard drive. So I'm getting into some territory here. I'm just not 100% sure about how this all works, and there's more optimizations could help. Here's another optimization I did. If max boot speed is set to 0, then it does this whole blanking of the screen, I guess the BIOS screen or whatever. But if it's set to 1, it skips over this whole section. So you can ignore these if-elses. That's not happening. I think it's this right here. So this whole section of code is not running when that's set. And the weird thing is, you can see there's no garbage on screen. It doesn't actually require it to clear the screen. So this is like superfluous code anyways. I feel when the CGA card is initialized, that initialization routine must clear the video buffer, which is why you don't really need to do this anyways. Now we're getting down near the end. So in max boot speed is set to 1. Remember, we get that quick beep at the very beginning of the boot process. So I remove the other beep so we don't have 2 beeps anymore. And then the next thing I'm changing is I'm altering the number of retries that it tries to boot from the floppy drive. It looks like the original retry, at least for GlaBIOS, is 3 times. I assume IBM is more, which is why it takes forever to end up in BASIC when you don't have a disk installed. And well, I end up changing this, and like I said, less retries, because why wait? So I think it just tries once, or it doesn't even retry one at all. It just tries to boot 1 time and then it gives up, and then we'll boot to BASIC or boot to the hard drive. And then one of the last things I'm doing as well, you might have noticed this, when I flip that switch on the motherboard and max boot speed's enabled, it won't even print that RAM 640K thing. Weirdly enough, it leaves a 16 up there, which has to do with that initial RAM test of just this first 16K, which I am still doing even with max boot speed, but the rest of it isn't even happening. And I felt that printing even that banner slows the system down even more, which is why I have this here. And I think I also changed it where you hit Control Delete, you don't get a beep, or maybe you get a quick beep. I can't remember what I did exactly. And that is it. Those are all the changes that we have here. Now let's go back to the keyboard reset routine here. So I know we have to kind of keep this keyboard reset stuff here. Set up and clear buffer, you're gonna need that, but probably need this whole section here. We gotta do this unmasked keyboard interrupt IRQ1. Now this is where I'm gonna make the big change. So what I'm gonna do is I'm gonna remove a whole big section of code here. So we're gonna put if max boot speed is there, and I'm gonna take out any of the max boot speeds that are in the middle of this. So we have ask the whole clear thing. I'm going to delete this. So this IO delay thing happens, some stuff happens. Check if the keyboard is happy. Well, it does a jump to it. Otherwise, it kind of does some more loops. Well, we don't want to do any of that. So I'm going to leave this code in. So I'm going to max boot speed is 0. It's going to run all this code. This is the normal code. And then what I want to do is we're just going to go here to endif, which this endif matches this if statement there. So if this is set to anything but 0, none of this code runs at all. None of this reset stuff. It's just going to jump right into this keyboard happy part. And then it's going to set up the real interrupt 9 keyboard interrupt handler. And then that's the end of the whole keyboard reset routine. So before I save this, I'm just going to make a backup copy, which I've just done. So we'll save that. Now let's run DOSBox so we can make this. And let's try running MAME just to see if it works in MAME. Now, MAME's not a great test to see if this really works on a real hardware, because of course we're changing hardware interface stuff with the keyboard routine, and it's not a good test. Oh, I don't want to run AliCat. So let's exit out of this. I want to go to BASIC essentially. So I'll just remove the floppy drive routine and we'll just run this again. Okay. Okay. And the keyboard doesn't even work. Even in MAME, it doesn't work. So that's really interesting. That little bit of reset code that I took out, the delay and stuff, prevents this from working altogether. And part of me wonders why. I wonder if it's this little section of code that we need to actually keep running. And I'm just looking at the code for keyboard happy. It doesn't look like any of this has to rely on anything that happens up here, but I wonder if we need this code. So I'm going to put an else statement there for max boot speed. So with the max boot speed set, it's just going to run this code, but none of these delays that are happening there are actually going to be taking place. Okay, so I just made the ROM again, and I can quickly start MAME. And this is why the iterative approach to using an emulator is so useful. No, it still doesn't work, even in MAME. That is wild. So there's no way this is going to work on real hardware, I'm assuming. So just for poops and giggles, let's change this to 1, and that means that the original code should now be running. Although I might need to go, you know what, I should go check to see if this is the original code. Let me go do that, because maybe I've altered this in some way. So this is the original code here. So this is everything between post keyboard test and end if before keyboard happy. Okay, so I just copied that into there. So now we have the stock code in place. I just assembled it with no issues. We'll start the emulator now. Okay. And the keyboard works. So definitely something in that code there that I did just cut out is necessary for the keyboard operation, at least on MAME. You know, I am curious. What if I change this? I'm going to change this back to 0, so I'm sort of removing all of this extra code. I'm wondering if this would work on real hardware, although I'm noticing here there's a pop, because this is using a stack, and maybe the stack is out of order and that's somehow breaking the keyboard. So keyboard delay, it looks like I'm skipping over that delay. I bet you that delay might be needed. I kind of want to get to the point where the code is working, at least in MAME, and then I can figure out exactly what breaks it. So all we have now is just this little section up here, not including this long delay and any of this stuff at the top. Let's see if that works. And I've changed this so max boot speed 0 is now running the original code, and everything below this else is the modified sped up code. Okay, is the keyboard going to work? Okay, so the keyboard is working now. Question is, should I remove this pop and the IO delay? Because it looks like this is used for the IO delay. And if we're not going to run that, then maybe I don't need that pop. What I'm doing here is I'm just showing you a little bit of example of like some of the work that I was doing to try to optimize this. And this is the amount of trial and error that I had to do, at least, because I don't fully understand how that initialization routine is working. So I don't exactly know what I can cut out. So the keyboard doesn't work again. So I don't know what I can cut out exactly to make it not work. It's good that MAME is a relatively accurate emulator because, you know, that change there is what broke the keyboard just now. So I'm wondering if I can have the pop in there, but I can take this IO delay out and have the keyboard still work. And then I need to test to see if this actually works on real hardware, especially with the Model F. Ultimately, I think what I need to do is, now the keyboard still doesn't work, I think I need to make it where this routine is optimized where it can work without a Model F, but then also you have a different setting that's like safer for Model F keyboards or slow keyboards. So I'm just going to go back to the bare minimum of the code that seems to be necessary, including, unfortunately, this annoying IO delay. So the funny thing is, I'm trying to find where this IO delay is in here, and I can't find it. So for instance, IO delay long, and I see what this does is when this runs, it does output to the CX register, which is why we had to pop CX onto the stack. But the weird thing is, I can't really find where this IO delay is referenced. It's used all over the place, but I don't see it as a macro. So I'm a bit confused. There's a proc, but I don't think that's the one. Okay, well, I can't really find where IO delay is, but I know if I take it out, the keyboard breaks, at least in MAME. And I know if I take it out and I don't pop CX, then the keyboard still doesn't work either. So I'm not 100% sure what's happening there, but I do know that MAME does work with the keyboard. So what I need to do is I need to load this code into the system, into the one ROM, so that we can see if this works with a real Model F or not. And here we go. Let's turn on the system. Okay, I still have the disk on ROM there. Okay, so the keyboard is working. I'm going to go to basic, so it emulates exactly what we had in MAME. Okay, that seemed really quick, didn't it? Although, what was I was getting like, what, 1 point something seconds, 1.2 seconds before anyways. Okay, Model F keyboard, that's what we need to test with. Let's plug this in. Okay, here we go, 3, 2, 1. Oh, it works. Wait, this works? Okay, interesting. Well, maybe there's enough of a delay that's still in there. I'm not sure. I thought I took most of that stuff out. Let's check if this boots into DOS properly. So we'll pop the disk on ROM in there, see if we get to MS-DOS. It's so funny because I really was sure that this wouldn't work, because I swear I did testing before and it didn't. I would get like garbage, but maybe that was just well, it could be that this keyboard connector is the problem. This keyboard connector has seen better days. It has really, really seen better days. So I just plugged the keyboard in, I hot swapped it. Yeah, and it's still working. Let's Control-Delete. Look at that, totally works. Let's change the switch from 1 to 0, and I'll power cycle the computer. So that means it's gonna try to initialize the floppy drive now. Well, it doesn't seek the floppy drive, it tries to boot the floppy drive. Okay, that works. I'm gonna take DOS 1.1. I'm gonna put that in the floppy drive. What I'm not 100% sure of, I haven't done extensive testing on this ROM. I'm gonna power cycle the computer. Okay, so that's interesting. The disk on ROM overrides the floppy drive, which I don't know if that's desirable or not. Floppy drive is obviously gonna be working still. So there it is. But I'm pretty sure if I pull the disk on ROM card out and we turn on the system, should boot off the floppy drive. Oh, it didn't boot off the floppy drive. Okay, so I broke something. Yeah, it boots very, very quickly, doesn't it? And it does initialize the disk, like the light comes on, but doesn't actually try to boot. So what did I do exactly? Well, I made a change, obviously, that stopped the boot process, and it gets into BASIC very quickly. Let's try AlleyCat, just in case I damage this disk maybe. Nope. Okay, well, I obviously have some more work to do to get this thing dialed in exactly where everything works. The floppy drive loads, the XT IDE works, these option ROMs work, the keyboard works reliably, all of those things. What I'm gonna do when that's done, I'm gonna talk to Greg, just make sure everything is good with me uploading a copy of the super fast assembly code somewhere, because obviously there's a GPL v3 license and I don't have the banner showing anymore and stuff like that. So I'll talk to Greg about that. I'm gonna upload it somewhere so everyone can take a look at it, and I will put a link to the .rom file so you can just download it yourself. But if you'd like to play around with this code yourself, check out the GitHub repo for GlaBIOS, because it has very good instructions on how you can assemble everything and use DOSBox to do it and stuff like that. I would love to beat the speed of the Tandy 1000 RL with the floppy drive still enabled, because right now the only way we can get, well, even match the 1000 RL is with the floppy drive disabled. Hopefully people watching know more about optimization of code than I do and can take the stuff that I've done and go way beyond and speed this up even faster, because I'm sure I've left stuff on the table that we can remove to make this go even quicker. And then, honestly, if I get this working, I'm going to take this BIOS and I'm going to install it into my actual IBM PC 5160 and my 5150, which incidentally, it doesn't work right now. I have to fix that thing, because I want those computers to be nice and fast for when I actually go to use them, which is occasionally. And to be honest, I have a few other XT motherboards I kick around like I use for testing and stuff. I'm going to put this ROM on those as well, because I love how fast this thing is. This is how fast the system should have been from the very start. And as I said, IBM should have made it where you just set that switch to 1 for comprehensive diagnostics or back to 0 for high speed. I don't know why they didn't just do that from the factory, but anyways, they wanted to make it a reliable computer. But I feel that this is perfectly reliable and it's fast now, which is awesome. So there we go. I hope you enjoyed this video, me fooling around with this stuff. This is not the normal stuff I did, because obviously I didn't fix any hardware in this video, but I kind of love this type of hacking. And I know no one really cares anymore, right? Like, who's using these computers except for like maybe Jim Leonard doing development work on the IBM. So this BIOS, though, is an awesome project. If you have an XT clone and you want a better BIOS, check out GlaBIOS. Even unmodified, it is so much better than any of those BIOSes that are out there. And of course, open source, GPL v3, you can edit yourself. There's just so many great things about it. And also check out the OneROM. What an amazing project. Thank you very much, Piers, for sending me a bunch of these to play around with. I gotta say, I am super impressed with that project, and I can't wait to see where it leads, because Piers is adding a bunch more capabilities to OneROM in the future that is gonna make it even better of a project. So if you like this video, thumbs up would be appreciated. If not, you know what to do. Huge thanks to my supporters, names go on the side of the screen, and all the other YouTube stuff. And I guess that's gonna be it. So stay healthy, stay safe, and I will see you next time. Bye-bye. So my IBM PC 5150 and the IBM 5153 CGA monitor, I haven't turned either of these on in a good while. They both were working fine last time I used them, but I have no idea about now. So first I'm going to turn on the monitor. I do have the power switch turned off, so let's turn this on and see if this starts up without any issue. Should give us a white screen if it's working. Okay, we have normal high voltage, so that's good. I don't remember if I've ever looked inside of here to see if I have any refas or not. So there might be refas. Oh, you know what? I have looked inside of here because I've actually swapped the CRT on this. The original CRT was very, very worn out. Okay, everything looks really good on the monitor, so that's excellent. Now we're going to turn on the computer. 3, 2, 1. Okay, that's a good sign. That's normal. Oh, yes. Okay, so we got a cursor, so the system is initializing. That's excellent. Let's make sure this actually works. Oh. Okay, well, clearly we have an issue. Yeah, repair video required for my good old trusty 5150. And this is one of the Rev A machines that's got the motherboard that's 16K to 64K motherboards. So very early machine. And well, yeah, okay, there we go. I'm glad the monitor works. I mean, it's turned on at least. So the power supply is working. It did actually seek. So it almost felt like it tried to boot. Let's, I can't reboot. You can't do Control-Alt-Delete if you have the parity check error. So I went and grabbed my IBM PC XT, the 5160, and I haven't turned this on yet because one of the issues with this machine potentially is that it's got an MDA card inside and doesn't have a CGA card. I don't have my MDA monitor handy. I want to use the CGA monitor for this video. So I think I will have to, I just have this disk in there sideways as a kind of placeholder for the double-sided floppy drive. I'm gonna need to open this thing up and take a look inside and just see what kind of video card's in here. Okay, I opened up the XT and it does appear that it has a CGA card. It actually has a multifunction IO type card. It has a hard drive controller, or sorry, floppy drive controller, clock battery port, and a CGA card built into it. Inside this machine was the original IBM hard drive controller, which is made by Xebec, and the original hard drive, which is a giant mini scribe. I don't know if that's original to the machine or not, but I don't need a hard drive in this machine for this demonstration, so I'm just going to pull out that hard drive card, and we're going to see if this thing works. What is this weird purple cable connected to the power supply? It seems to be a ground lug that makes its way to the hard drive. Okay, that must be some weird IBM thing. And this does appear to have the original IBM power supply in here, but look, it says NWA, a division of Photo and Sound Company, 820 Northwest 18th, Portland, Oregon, 97209, and a phone number. So I guess they were the owners of this particular computer, or perhaps they are who serviced this machine at some point. Now, one of the issues with these types of machines, if you haven't used them in a while especially, is that the tantalums have a tendency to go, and these are the ones on the motherboard. The power supply in these, I think, is smart enough to shut off so it won't just cause some kind of sparks, but you never know. So we'll turn on the monitor. So it's on, it's plugged into the back of the computer into this multifunction card. I don't have the keyboard connected up, but let's see if this works. And hard drive is connected to power, by the way. So we'll hear that go unless we get sparks. Okay, the hard drive is spinning up. That's cool. Oh, we got a 301 error. I think that's the keyboard not connected. All right, so hopefully this thing can boot. Let's take this placeholder floppy out of there. Alrighty, error, F1 to resume. I'm going to put a disk in here to see if this thing can boot into DOS without the hard drive connected. I will need to plug in the keyboard, so I'm just going to use this random Model F that I have sitting around. This has a very chewed up power cord, or data cable, I mean. I have a replacement cord for the Model F, I just haven't fitted it. Okay, so you got a power cycle of the computer. When you plug one of these in, pretty sure it doesn't support hot plugging like later PCs. Yeah, okay, no error. Excellent, I think this machine is actually going to work. Oh yeah, this hard drive, by the way, you probably won't be able to see it on camera, but the IBM front plate here actually has IBM logo on it, as does the floppy drive. So these would have been the original fitted drives for this machine. All right, it looks like it's booting. There we go. Although we don't have a functional keyboard. There's some junk characters typed there. That's strange. What is happening here? Typical vintage computer problems we're having here. So I know this Model F works. I just used it the other day. I checked that it was seated in the back of the computer properly, and it, without a doubt, is plugged in correctly. I'm gonna have to power cycle the computer here, and we're gonna see if it, well, I mean, we didn't even get the keyboard error on the monitor, the 301. So it's seeing the keyboard, but why am I not able to type? That is the question. Also, I'd like to unplug this hard drive, but in typical fashion of these machines, I can't easily do that because the power connection is up against the power supply. I'd have to remove the drive to even unplug it. Working on this original XT case that IBM designed, sometimes it's not super easy. Now it's working. I just had to reseat the connector, I suppose, in the back of the computer. Probably needs a little bit of deoxit. That probably would make it work. All right, well, I'm happy to know that my 5160 is working properly, and so is the monitor and the floppy drive and the keyboard. So now I can go on and make the rest of this video, and I'll probably just put this little thing at the very end as sort of like bonus footage, bonus content, that kind of thing. Pew!